Have you ever stared up at the night sky and felt that sense of infinite possibility, that feeling that there's so much more out there than meets the eye? What if I told you that feeling, that deep-seated human curiosity about the unknown, just led us to what might be the biggest astronomical discovery of our lifetime, hidden right in our own cosmic backyard? We're talking about a world possibly as large as Neptune, lurking unseen, unfelt, until now. Forget grainy photos or ambiguous blips. Imagine evidence unearthed not just by human eyes, but by the processing power of a quantum artificial intelligence, sifting through the most advanced telescope data ever gathered. This isn't just a theory anymore. This could be the moment Planet 9 steps out of the shadows. For years, the concept of Planet 9 has been the stuff of astronomical legend, a massive, phantom world gravitationally bullying tiny objects in the Kuiper belt, that icy debris field beyond Neptune. Scientists like Mike Brown and Konstantin Batygin at Caltech laid out the compelling mathematical case back in 2016. Something big had to be out there, orchestrating the strangely clustered orbits of these distant Trans-Neptunian objects, TNOs. Think of it like noticing a pattern in how leaves are scattered in one specific corner of a vast park. You might not see the wind, but you infer its presence and direction from the effect it has. That's been the hunt for Planet 9, inferring its presence from its subtle gravitational whispers across billions of miles. Countless hours of telescope time, sophisticated simulations, and sky surveys have been dedicated to finding direct proof, a single point of light betraying its location. But the sheer scale of the outer solar system is staggering. Imagine searching for a single dark bowling ball hidden somewhere in an area the size of North America, using only a dim flashlight. That's the challenge astronomers faced. The distances are immense, the potential locations vast, and any reflected sunlight reaching us would be incredibly faint. But then came the James Webb Space Telescope, JWST, a marvel of engineering designed to capture the faintest infrared light from the dawn of the universe. Its primary mission wasn't Planet 9, but peering into the cosmic dawn, observing the formation of the first stars and galaxies. To do this, it takes incredibly long exposures, deep field scans, sometimes staring at seemingly empty patches of sky for hours, even days. These scans, while aimed at distant galaxies, inevitably sweep across the foreground of our own outer solar system. Within this flood of data, this digital treasure trove capturing infrared whispers from across time and space, lay countless images of faint, distant objects, asteroids, Kuiper belt objects, and potentially something more. These weren't just pretty pictures. They were terabytes upon terabytes of raw data, filled with instrumental noise, cosmic ray hits, and the faint signatures of countless known and unknown objects. To the human eye, or even traditional computer algorithms, searching for Planet 9 in this data deluge was like trying to hear a single specific heartbeat in the roar of a stadium crowd. The signal, if it existed, was buried deep within layers of cosmic and instrumental noise. It was a pattern waiting for a new kind of perception. Enter the breakthrough, a quantum AI system. Now, let's unpack that because it sounds like science fiction, but the principles are grounded in cutting-edge physics and computer science. Classical computers, the ones we use every day, process information in bits, either a 0 or a 1. They analyze data sequentially, pixel by pixel, step by step. It's powerful, but for certain types of problems involving immense datasets and complex pattern recognition, it can be slow and inefficient. Quantum computing operates on entirely different principles. It uses qubits, which can be 0, 1, or both simultaneously, a state called superposition. Furthermore, qubits can be linked together through a phenomenon called entanglement, where they remain connected no matter how far apart they are, sharing the same fate. This allows quantum systems to explore a vast number of possibilities simultaneously. Instead of sifting through pixels one by one, This quantum AI leverages these principles, quantum probability and entanglement, to analyze relationships and patterns across the entire dataset at once. It doesn't just look at the data, it interacts with the probability space of the data, calculating the likelihood of different configurations of light and gravity across enormous regions of space. Think of it like this. A classical computer trying to solve a maze explores one path at a time, hitting dead ends and backtracking. A quantum computer can, in a sense, explore all paths simultaneously to find the solution much faster. For 72 relentless hours, this quantum AI system immersed itself in the JWST deep field data focusing on the outer solar system. It wasn't just looking for a bright spot. It was calculating the subtle gravitational tug-of-war between all potential points of mass, correlating that with the distribution of faint infrared light detected by Webb. It was searching for a consistent gravitational influence that couldn't be explained by known objects, and looking for a corresponding faint heat signature. And then it found it. A recurring, slow-moving signal emerged from the noise. Not a glitch, not a random fluctuation, but a persistent signature. This wasn't just a single detection. It was a pattern observed across multiple datasets, consistent over time. The AI identified a shadowy object, as the original report put it, whose gravitational presence was subtly warping the predicted paths of nearby, smaller Kuiper belt objects, like unseen footsteps leaving faint impressions in the snow. Crucially, alongside this gravitational evidence, the AI detected a faint but consistent infrared reflection, heat, emanating from a precise region of space where no known star, galaxy, or asteroid existed. This infrared signature wasn't bright, but it was persistent, a ghostly echo in the cold darkness. When the intensive processing concluded, the system's final output was chillingly simple, devoid of fanfare, yet earth-shattering in its implication. Anomaly confirmed. Candidate object detected. For the scientists monitoring the system, this wasn't just another data point. Initial skepticism quickly turned into stunned silence, then feverish activity. This wasn't an artifact of the processing, an over-enhancement of random noise. Cross-checks and validation runs confirmed it. The quantum AI had isolated a coherent pattern, a convergence of gravitational influence and infrared emission that precisely matched many theoretical predictions for Planet 9. The preliminary analysis suggests an object with a mass somewhere between 5 and 10 times that of Earth. This fits squarely within the range predicted by the Caltech astronomers needed to explain the TNO clustering. Its inferred orbit is vast, highly elliptical, likely taking tens of thousands of years to complete a single journey around the Sun. This explains why it remained hidden for so long. It spends most of its time incredibly far away, reflecting negligible sunlight and emitting only faint thermal radiation. This potential discovery isn't just finding another rock. It's potentially finding the missing piece of the puzzle that explains the strange architecture of our solar system's outermost edge. Self-reflection pause. Isn't it incredible how a theoretical prediction, born from observing subtle patterns in orbital mechanics, could lead us here? It reminds me that sometimes the biggest truths are hidden in the smallest details, the anomalies that don't quite fit. It takes persistence and new ways of seeing, in this case, quantum AI, to bring them to light. How often in our own lives do we dismiss small inconsistencies, overlooking patterns that might point to a deeper reality? This kind of science, pushing the boundaries of observation and computation, is what fuels our understanding of the cosmos. If uncovering these deep cosmic secrets excites you as much as it does me, make sure you subscribe and hit that notification bell. We explore groundbreaking discoveries like this every single week, and you won't want to miss what's coming next. Okay, let's dig even deeper. This potential Planet 9 isn't just a single point of light. It's a convergence of theory, observation, and cutting-edge technology. Remember, the Planet 9 hypothesis wasn't just a wild guess. It stemmed from that baffling observation. Why do so many distant, icy bodies, TNOs, beyond Neptune share remarkably similar, tilted, and elongated orbital characteristics? It's like finding a dozen compass needles all pointing slightly away from true north in one specific area. You'd suspect a hidden magnetic influence nearby. Planet 9 was proposed as that hidden gravitational magnet, subtly shepherding these TNOs over billions of years. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared spectrum, was seen as our best hope to finally spot this elusive world directly. Infrared is key because a distant planet, far from the sun's warmth, would be incredibly cold, emitting most of its faint energy as heat, infrared radiation, rather than reflecting visible light. But even for Webb, the challenge remained immense due to the sheer volume of data and the faintness of the potential target. This is where the quantum AI's approach becomes truly revolutionary. It's not creating a sharper photograph in the traditional sense. Forget about zoom and enhance. Instead, it operates in the realm of probabilities. It constructs probability fields, complex maps predicting where the faint light from a hypothetical distant object should appear based on theoretical models and known physics. It then meticulously cross-references these predictions with the actual faint light detected by Webb and with the subtle gravitational anomalies inferred from the movements of other known objects in the region. Imagine trying to find a specific person in a massive, dimly lit crowd, but instead of just looking for their face, you also have sensors detecting the slight shifts in movement of everyone around them caused by their presence. The AI is doing something analogous on a cosmic scale. It's building a statistical reconstruction, a dynamic model that evolves over time, showing not just where the object likely is, but how its presence influences its surroundings. It's less like taking a single snapshot and more like building a constantly updating weather map, revealing the pressure system, gravity, and temperature, infrared signature of this hidden object. This marriage of quantum computation, designed to handle immense probabilistic calculations, and Webb's exquisite astronomical data is what allowed this potential breakthrough. It's a glimpse into the future of scientific discovery, where AI doesn't just analyze data, but helps us perceive patterns hidden within the fundamental fabric of reality. Now the billion-dollar question: what is this thing? The data is compelling, the anomaly confirmed, but its precise nature is still under intense debate. Two primary theories dominate the discussion. Theory A, the conventional planet. This aligns most closely with the original Planet 9 hypothesis. The object could be a conventional planet, albeit one unlike anything in the inner solar system. Given its estimated mass, 5-10 times Earth's, it's likely an ice giant, similar to Uranus or Neptune, or perhaps a super-Earth with a thick gaseous envelope. Its formation story is debated. Did it form closer to the Sun and get ejected outwards during the solar system's chaotic youth, or did it form in situ in the cold depths of space? Its slow, highly elliptical orbit, taking it perhaps hundreds or even thousands of times farther from the Sun than Earth, would explain its chilling temperature and why it evaded detection for so long. If this theory holds, it fundamentally changes our census of the solar system. We'd have a new, massive member in the family, forcing us to revise our models of how planetary systems form and evolve. It would confirm the power of gravitational inference and finally solve the TNO clustering puzzle. Theory B, the primordial black hole, PBH. This is where things get truly exotic. Some scientists propose that the object might not be a planet at all, but a primordial black hole. These aren't the black holes formed from collapsing stars. PBHs are theoretical objects thought to have formed from density fluctuations in the extreme conditions of the very early universe, just moments after the Big Bang. They could potentially have masses ranging from that of an asteroid to thousands of times that of the Sun. A PBH with the mass of 510 Earths would be incredibly compact, perhaps only the size of a grapefruit. Yet, it would exert the exact same gravitational influence as a planet of the same mass. This could explain why it's been so hard to see directly. Furthermore, while black holes don't emit light themselves, the quantum AI detected an unusual infrared signature. Could this be related to faint radiation from matter accreting onto the PBH, though unlikely for such a small one in empty space? Or perhaps Hawking radiation, a theoretical emission from black holes, though expected to be incredibly weak for this mass? Or could the PBH's gravity be subtly lensing background light in a way that mimics an infrared source under the AI's analysis? Discovering a PBH within our own solar system would be revolutionary beyond measure. It wouldn't just rewrite planetary science. It would provide the first direct evidence for these elusive objects, offering a window into the physics of the early universe, and potentially even shedding light on the mystery of dark matter, as some theories propose PBHs could constitute a fraction of it. Both possibilities are staggering. A new planet reshapes our solar system's story. A primordial black hole reshapes our understanding of cosmology and fundamental physics. The crucial point is that the quantum AI's analysis, integrating gravitational and infrared data, points unequivocally to a massive, dark object influencing the outer solar system in a way nothing known can explain. It's a game changer, regardless of the final identification. But hold on, the plot thickens. As if discovering a potential Planet 9 or PBH wasn't enough, the quantum AI analysis revealed an unexpected, almost unsettling twist. The object's movement, its gravitational influence, doesn't perfectly match the smooth, predictable path expected even for a massive hidden object. There's a wobble, an irregularity in its motion, subtle deviations from the simulated orbit that hint at something more complex than a single, isolated body. What could cause this wobble? Several possibilities are being explored. A companion. The object might not be alone. It could possess its own moon, or even a system of moons. A sufficiently massive moon orbiting Planet 9 would cause it to wobble around their common center of mass, adding complexity to its overall gravitational signature detected by the AI. Rings or debris field. Like Saturn, the object might be encircled by a substantial ring system, or perhaps a dense cloud of captured debris. The uneven distribution of mass in such a system could introduce irregularities into its gravitational field. Interactions with other unknowns. Could this object be interacting gravitationally with other, smaller, yet undiscovered bodies in the extreme outer solar system? Perhaps the Kuiper belt is even more dynamically complex than we imagined. And then there's the other anomaly, something even more intriguing and admittedly highly speculative. The AI detected a subtle, rhythmic pulsing in the object's faint infrared heat signature. A narrowband reflection seemed to wax and wane at regular intervals. Now, many scientists urge caution. This could easily be an instrumental artifact, some previously unknown natural phenomenon related to its rotation or atmospheric dynamics, if it's a planet, or perhaps interaction with the interstellar medium. Natural explanations are usually the most likely. However, the regularity of the pulse has inevitably sparked wilder speculation. Could this pulse be artificial? The idea that this object might be something other than a natural planet or PBH, perhaps an ancient technological artifact, a derelict megastructure, or something truly alien is, of course, extraordinary and requires extraordinary evidence. It's firmly in the realm of speculation. Yet the AI detected the pulse. It's part of the data signature. This twist, the wobble and the pulse, forces us to confront the possibility that the outer solar system harbors complexities far exceeding our models. Every deviation from expectation, every unexpected signal, is a clue. It tells us that even if this is just Planet 9, its story might be far richer and stranger than we anticipated. Another pause for thought. This reminds me of peeling an onion. You think you've reached the core only to find more layers underneath. It's a lesson in humility, isn't it? Just when we think we have a grasp on things, the universe throws us a curveball, a wobble, a pulse, reminding us how much more there is to learn. It encourages us not to settle for the first explanation, but to keep probing, keep questioning. If you've journeyed with us this far into the cosmic darkness, you're clearly someone who isn't afraid to explore the profound mysteries of existence. Hit that like button if this exploration is blowing your mind. And I genuinely want to know your thoughts. Drop a comment below. Based on the evidence, what do you think is lurking out there? A hidden ice giant? A grapefruit-sized primordial black hole? Or could the wobble and pulse hint at something else entirely? Let's take a breath and absorb the magnitude of this moment. We are potentially standing on the precipice of confirming a new world in our solar system, a discovery driven by the synergy of our most advanced observational tool and a revolutionary computational intelligence. Every faint gravitational nudge recorded in the orbits of distant ice balls, every stray infrared photon captured by Webb's mirrors, every subtle anomaly teased out by the quantum AI. They are like cosmic breadcrumbs, leading us down a path towards something monumental. This isn't just about updating textbooks or adding a new name to the planetary roster. It's about fundamentally expanding our perspective. For centuries, we've mapped our solar system, believing we had a decent handle on its major constituents. This discovery, if confirmed, tells us there are still giant secrets hiding in plain sight, obscured only by distance and darkness. It underscores the vastness not just of space, but of our own ignorance. But it's a thrilling ignorance, one that beckons us forward. What does this mean for our place in the cosmos? It suggests our solar system might be more dynamic, perhaps more crowded, than previously thought. It adds a new character to the celestial drama, a massive, enigmatic player whose influence has shaped the fates of countless smaller bodies over eons. Whether it's a planet formed alongside its siblings or a captured wanderer from interstellar space, its presence forces us to reconsider the narrative of our solar system's formation and evolution. Digging deeper, the speculation doesn't stop at just Planet 9 or a PBH. Some theorists are now revisiting other intriguing ideas, energized by the quantum AI's findings. The captured rogue. Could Planet 9 be an interloper? A rogue planet formed around another star and ejected into interstellar space that drifted too close to our sun billions of years ago and was gravitationally captured. Our galaxy is likely teeming with such homeless worlds. Finding one in our own system would provide invaluable data on these objects and the chaotic processes of planetary system formation and disruption. The AI's analysis of its potentially irregular orbit might lend credence to this capture scenario. The stellar remnant. Another, perhaps less likely but fascinating idea, is that the object could be the remnant of a tiny, failed star, a brown dwarf, or even the collapsed core of a very small star that died long ago. Such an object could possess significant mass and emit faint infrared radiation. If it wandered into the sun's gravitational influence, it could have been captured into a distant orbit. This would blur the lines between planetary and stellar objects and suggest a history of interaction with passing stellar neighbors. These additional layers of speculation highlight how dynamic the scientific process is. The new data isn't just answering old questions, it's prompting entirely new ones. Researchers worldwide are now comparing the specific gravitational and infrared signatures identified by the quantum AI with data from other star systems. Are there similar anomalies lurking around other stars? Could massive, unseen objects in the far reaches of planetary systems be a common phenomenon, rather than an exception? The quantum AI hasn't just given us a candidate, It's potentially given us a template for finding similar hidden giants elsewhere in the galaxy. The debate is fierce, the analysis ongoing, but one thing is becoming increasingly clear. Our solar system, and perhaps most solar systems, are likely far more complex and surprising than our neat models have allowed. And perhaps the most stunning piece of the puzzle provided by the quantum AI system wasn't just the what, but the where. Its final simulation didn't just say, "There's something out there." It pinpointed the object's predicted current location with astonishing precision, narrowing it down to a patch of sky just 0.3 degrees across. That's slightly larger than the apparent size of the full moon, but for the vastness of the outer solar system, it's an incredibly small search area. How did it achieve this? By synthesizing all the data, the gravitational perturbations of multiple TNOs over time, the faint infrared signature, its subtle movement across different JWST observations, even factoring in minute variations in the cosmic infrared background. The AI built a predictive model of the object's orbit and current position, constantly refining it as it processed more data. Its final confidence score in this location prediction: a staggering 97.2%. While not 100%, that level of confidence from such a sophisticated analysis is practically shouting at astronomers, "Look here." Imagine the excitement in the closed-door briefings. According to internal sources, one leading astrophysicist remarked, "If this data holds up and we find it where the AI predicts, then our understanding of outer solar system dynamics, formation, everything, it needs a fundamental rewrite." The reported silence from official channels like NASA isn't necessarily skepticism. It could well be the sound of intense verification and preparation for an announcement that could shake the foundations of planetary science. This final prediction ties everything together, from Webb's raw infrared light through the quantum AI's pattern recognition and probabilistic modeling, incorporating gravitational whispers and subtle heat pulses, emerges a specific target. We may finally have a map to find the treasure. So, where does this leave us, humanity, looking out at the vast cosmos? This potential discovery is far more than just an astronomical footnote. It represents a profound leap in our ability to perceive the universe. The combination of JWST's unparalleled observational power and the analytical capabilities of quantum AI has opened a new window onto the cosmos, allowing us to detect signals and patterns previously lost in the noise. We are developing tools that can see the unseen, compute the incomprehensible, and reveal secrets hidden in the fabric of spacetime itself. This isn't just about finding Planet 9. It's about demonstrating a new paradigm for discovery. Imagine using similar techniques to analyze exoplanet atmospheres for faint biosignatures, or sifting through gravitational wave data for echoes of the Big Bang, or even, perhaps one day, detecting unambiguous technosignatures, signs of advanced extraterrestrial technology. The possibility, however remote, that the rhythmic pulse detected from this object could be artificial, though again, natural explanations are far more probable, serves as a tantalizing reminder that the search for life and intelligence elsewhere is intertwined with our exploration of fundamental physics and cosmology. For scientists, this is the dawn of a new era. The ability to cross-correlate multi-messenger data, light, gravity, maybe even neutrinos or gravitational waves in the future, using AI trained to recognize complex, nonlinear patterns will undoubtedly lead to discoveries we can barely imagine today. For all of us, it's a powerful reminder of the enduring power of human curiosity and ingenuity. We build incredible machines, develop revolutionary algorithms, all driven by that fundamental desire to understand. What's out there? How does it work? And where do we fit in? Standing at this threshold, potentially welcoming a new, massive member to our solar system family, offers a profound lesson. For years, Planet 9 was a ghost, a mathematical necessity whispered among astronomers. It took persistence, the development of revolutionary tools, JWST and quantum AI, and the willingness to look deeper into the noise to potentially find it. How often in our own lives do we encounter anomalies, situations that don't quite fit, feelings that seem out of place, subtle patterns we dismiss as noise? This story reminds us to pay attention to those whispers. Sometimes, the most significant truths aren't shouted from the rooftops. They're hidden in the data and the inconsistencies, waiting for a new perspective or a more powerful tool, perhaps introspection, empathy, or critical thinking, to bring them into focus. It teaches us the value of challenging assumptions, of embracing complexity, and of having the courage to explore the unknown territories within ourselves and the world around us. The universe, and perhaps our own potential, is far richer and more mysterious than we often assume. Don't be afraid to look for the hidden planets in your own life. You might be surprised by what you discover. What aspect of this potential discovery fascinates you the most? Is it the sheer scale of Planet 9, the exotic possibility of a primordial black hole, the power of quantum AI, or the mystery of the wobble and pulse? Share your thoughts below. Before you go, I want to sincerely wish you good health and a clear mind, ready to explore the wonders both out there in the cosmos and within your own life. The journey is far from over. If this glimpse into the cutting edge of space exploration has sparked your curiosity, make sure you subscribe and turn on all notifications. Our next exploration promises to be just as mind-bending, as we delve into the mystery of an ancient star that seemingly defies the laws of cosmic time. You won't want to miss it. Stay curious, stay questioning, and I'll see you in the next exploration.